Hello and welcome back to the lab. Today we're going to be talking about the last major step remaining on my Ethernet switch project before ordering the final PCB, namely signal integrity optimization. So if you're not already following some of the progress updates on my Mastodon and my blog, just to give you a quick summary, this has been in the works for, I believe, 13 years at this point. 2013 roughly is when I started being interested in building my own open hardware Ethernet switch. I've had lots of detours over the years as I realized I was missing this or that piece of test equipment, or just had no idea what I was doing, or my initial prototype, the FPGA, was too small, and so I've matured a lot as a hardware designer, as an FPGA designer, written protocol decodes for pretty much every flavor of Ethernet under the sun for ngscopeclient. Gee, I wonder why those exist. So now here we are where I'm finally ready to start putting it all together. I've proved out a lot of portions of the switch fabric on subscale projects. I've already brought up and validated the line card, the intermediate bus converter, and the power distribution board. So all of these boards you see in the CAD model here already exist and are tested. I have not fully populated all of the line cards. I've only brought up one of them, so I just got to go do a run of the pick and place to stuff the rest of them. But ultimately, my hope is to have two of these running production, pushing packets in my lab in the next probably year at this rate, hopefully. I don't know. I've waited 13 years, so it'll take as long as it takes. And then finally off on this side is just a little carrier that has the two SFP28 uplinks. So in total, we've got two line cards with 24 1 gigabit Ethernet ports on each one base T. So total of two line cards, 48 base T ports, and then the two SFP28 uplinks. And then not yet shown on the back side of the enclosure is going to be the 1 gig Ethernet port for management, separate from the front panel fabric ports. There's going to be a serial port for initial IP configuration and so on, and then the 48 volts DC power input going into the intermediate bus converter. That is going to step it down to 12 volts to run everything else internally, and then some airflow vents for fans and so on. I still have to work out all the thermals, and at a rough level, there's going to be intakes here and kind of T-shaped vents, so air is going to come in from the left and right and then out the back, just because there's not really enough space in the front panel to have intake. And this is meant for use in my rack at home, not in a data center with a whole bunch of dedicated hot and cold aisles and so on. So this made more sense for a thermal design for this use case. Anyway, so what's missing, the only board that doesn't yet currently exist, is this section right here, and that is where the main logic board is going to go. So that has been in the works for quite some time as well, as you might notice from the June 2025 date on the silk screen from when I mostly finished the layout. And then life got in the way and I never had time to finish signal integrity sign off and design review. And so now fast forward 11 and a half months and I'm back and ready to go put the last couple of finishing touches on it and send this board out for manufacture pretty soon, hopefully by end of the month, but we'll see. So high level overview here. On the left side, we've got the 12 volts in on a Molex mini-fit connector coming in from the PDU board. We've got a couple of PMODs just for debug purposes. It's always nice to have extra GPIOs. Debug JTAG trace connector for the main processor. This is an STM32H735, so 500 megahertz Cortex M7, half a meg of SRAM, a megabyte of flash. Way overkill for just running an SSH interface and a few other things, but it's fast, and I didn't really want to be bogged down waiting 100 milliseconds for an SSH session to start up or something like that. So I wanted something with a little bit more horsepower and enough capabilities that I was not going to have to go back and run into problems because I hadn't given a fast enough CPU or enough flash or whatever. And then hiding up here, we've got the 5 for the management interface. This is just a KSD 9031, nothing special. The serial port for the management interface. Then up here, there's an STM32L431 that's acting as a PMIC supervisor, runs all the power rails, resets, does all the sequencing, etc. Then all of the debug for the supervisor, and off on the side here are the main high power switching converters. These are all Murata MY-MGK series. You'll notice a couple different sizes here for the different power domains with different requirements, and then a little LDO for a 2.5 volt rail and another LDO for VCC aux on the GTYs. Then this is the boot flash for the FPGA, some I2C interfaces for talking to the various other boards in the chassis, And then under the heatsink here is the core of everything. This is a Kintex Ultra Scale Plus XCKU 5P FPGA that's going to contain the entire packet data path. And then coming down off here, you'll notice all the differential pairs on the front and a bunch more on the back side here are all of the high-speed SERDES. There are a total of 16 GTYs on the FPGA. We are running 12 of them as QSigmy, so this is a 5 gigabit differential pair carrying 4 1 gigabit Ethernet lanes plus protocol overhead going out to the line cards. So the line card has two 12-port PHYs on it, and each of these 12-port PHYs has 3 QSigmy lanes. So 3 transceivers going to each of these PHYs, 6 transceivers to each board. And to keep things simple and to not have to use a fancy low-loss laminate or have to worry about excessive loss on the SERDES and the line card, I decided to go with a Flyover topology. This design has gone through several iterations. The original concept called for a rigid board-to-board connection, a lot similar to like the old school SLI bridges that would have had like maybe a Samtec Q-strip or something going from here out to a backplane of the board and then from there out to the line cards. Earlier designs also called for 3 line cards rather than 2, and the geometry with my chosen PHY ended up working better having 2 line cards. Each of the PHYs on a line card has 3 QSigmy lanes, and so we're using the Samtec ARC6 series for the interconnect cables. These are slight overkill. They're rated for PCIe Gen 6 64 gig PAM4, so the insertion loss performance of these is really good. They have S parameters similar. I don't have it open right now, but anyway, the insertion loss of these over the links that I'm working with for QSigmy is going to be quite low. The only thing where the loss of the cable is really going to be that big a factor is going from here on the switches board. So these connectors here I didn't actually include in the case render just because the chassis designer software gets a little bit slow when you have too many polygons in some of the models, so I simplified the models for this. But anyway, these drills here, you can see these are where the ARC6s are going to connect to, and so we're going to have some fairly long runs going from here across the chassis to these, but these are only 5 gigabits per second, and then going out to the SFP28 uplinks here are going to be 25 gig NRZ, but that's a much shorter link. I could probably use like a 6-inch cable or something like that, and so the insertion loss is going to be obviously a lot less than in the cables going out to here. Anyway, so in total, we have 3 transceiver lanes going out to each PHY on the line card. These are actually 8-lane cables and connectors, so we're going to have 2 unused lanes, and then have 3 transmit and 3 receive going out to, this is line card 1, PHY 1, line card 1, PHY 0, line card 0, PHY 1, line card 0, PHY 0. And so in total, this is 3 lanes times 4 connectors is a dozen transceivers. We have 16 on the package, and we need only 2 going to the SFP28 uplinks. So I pinned out the other 2 to a spare connector. I don't intend to use these right now, but I always feel bad leaving transceivers not routed anywhere just because I never know if I'm going to find a use for them. I had thought about maybe running like a 40 gig QSFP as an option for the uplink instead of 2 SFP28s. And with these 2 connectors, there still is the option of making a slight change to the chassis and doing a QSFP on the uplink. I think I have enough front panel space, but for the time being, I'm doing 2 SFP28s for the uplinks. And now switching to the layout view, this is a 10-layer board using Taiwan Union TU-872 SLK for all of the high-speed signals. This is a moderately high-performance, low-loss dielectric. It's kind of like the Asian equivalent of FR408, so still has generally FR4-type processing capabilities. It's worse performance than something like Rogers 4350 or something like that, but still a significant cut above standard FR4 as far as dielectric loss goes. And then the internal layers between the power planes are just using Shengi S1000, nothing special. So moving down here to the transceiver area, which is obviously what we care about. This is really the only high-speed signals on the board. Nothing else is at all fast. I did break out the CDR recovered port from the transceiver quads just in case I wanted to go look at those in a scope or something like that, but I don't expect to use that outside of debugging and just curiosity, see how clean the recovered clock coming off the GTYs is. All this stuff over here is just like I2C and enable lines, nothing really have to care much about SI for. The argme is straightforward enough. This is pretty much copy-pasted from other validated layouts, so nothing to worry about there. And over here is the FMC. This is the parallel memory controller coming from the STM32 off to the FPGA. So the STM32 thinks the FPGA is a parallel PS RAM, and the FPGA has an IP block I wrote on it that bridges this parallel SRAM interface out to APB. And so essentially we have AXI on the M7 getting bridged out to this SRAM protocol and then back onto APB, and we have a somewhat indirect AXI to APB bridge straight onto the FPGA. It works really nicely. So now let's move on to the meat of what we're going to be talking about today, which is the transceivers coming off of the FPGA to these ARC6 connectors. So zooming in a little bit here, you can see there's actually two different layouts on the draft board. I left this on purpose because I had initially done a couple different variations of this layout coming here. For example, some of these transceivers made sense to route out in this kind of vertical linear fashion, and some of the ones coming out here in the original version of this design, I actually had all these transceivers routed out like this. So coming off of one board, you can see this is the transmit negative and then transmit positive coming off separately in a line, and then jumping down and then correcting for the phase mismatch here. This is not good, and we're going to see why, but I left it here on purpose just to show you and compare to what I've done on the lanes further to the right that I've already optimized. So over here we can see that the output of the transceiver comes sideways right off of the BGA pads and then hooks down to the south. And then we've got one small phasing bump down here, which I might fine tune a little bit. I still haven't simulated with some of the parasitics from the other balls here to see if I can get away with putting it up there. But the length or the phase mismatch from making this one small bend is much smaller from doing this. You can see how big these meanders here are compared to having this tiny bump here. The other thing you'll notice that I did on the newly redone layout here is that every time I have a bend, I put a meander right at the bend, and you'll see here, for example, I've got a meander on, this is the positive side here, and then immediately one on the negative side here. And so the goal is specifically to keep the phase matched all the way down the diff pair, rather than just maintaining the phase as being equal end to end. And this is important because this is a tightly coupled differential pair geometry. If you're using loose coupling, so for example over here coming off of the coupling capacitors on the recovered reference clock, which is also a much slower speed, you can see that I'm routing the positive line up here and the negative line here. They're taking very different paths. They're nowhere near each other. I've got a giant meander here and nothing on here in order to maintain the phasing as we get out to these SMPM connectors here that are meant for scope probes. But we are far enough away on, this is also on, I believe, 90 micron or 100 micron pre-prags. And so the traces here are 120 microns, so we're already more than one height wide right here, and so we're probably 10H at least out to the nearest trace. So these are a very loosely coupled pair. I didn't even bother to model the coupling. I just routed these as independent 50 ohm tracks, and the coupling between them is negligible. On the other hand, these guys down here, these are 79 micron tracks with 101 micron space between them. And so that is a much, much more tightly coupled pair. And so it is important to actually keep them phase matched as much as you can along the entire path so that you are actually coupling to a signal of equal and opposite magnitude. And then we can see as we get down here towards the connector, the tracks neck up a little bit so that we don't have as much of an impedance discontinuity at the connector. And then jumping down to the layer 2, I'm going to turn on zone filling here. We've got a ground plane void under the connector because this connector land is significantly larger than this is the size for a 50 ohm trace, this is the size for the tightly coupled differential pair. And then we can see going from this 50 ohm track up to here, the impedance of the pad is going to be like 30 ohms or something ridiculous like that. And so it is important to put this cutout here, and obviously I went through a couple different sizes and fine-tuned the geometry, and we're only going to talk about the front side stuff for the moment. We're going to worry about everything that's going to the back side separately. And then jumping up to here, looking at the BGA launches, we can see same thing. There are ground plane voids under the BGA lands, and the size of these is very important so that we don't have a low impedance discontinuity right at the launch. So now, without further ado, let's jump into Sonnet, and I will show you the 3 versions of the layout that I simulated. I tried to keep them as close as possible and only change one variable at a time. So first, there's this version. This is the actual, what I consider the good or final geometry that I intend to use on the board. And this is, if we look over here, we are looking at the uppermost trace. This is line card 050 lane 2 transmit. I chose this one mainly because it was a slightly shorter run, and the meshing that Sonnet uses is actually aligned, and it really does not like long diagonal runs, and this track didn't have too many diagonals compared to some of the ones like going out here had a lot more diagonals, and it would have just taken a lot more time to simulate. And so I'm focusing on trying to verify like these meanders and these curves are performing well, and that the launches at the start and the end are good, and then making the line a little bit longer. We just have to worry about slightly more potentially discontinuities at some of these meanders and slightly more insertion loss over the length. And so probably before I order the board, I may try and do a simulation of this entire line here, but certainly for prototyping the launches and tweaking stuff, it didn't make sense to try and do a lot of iterations on the longer stuff, just it would have taken too long. Anyway, so this is the version that I'm actually going to consider good, and this one you can see has the ground plane cutouts here and the ground plane cutouts down here. And here's the board stack up over here. We can see we're using the thick metal model on here, and then we're just modeling the first ground layer, and then not worrying too much about the stuff going further down because we are only doing front side tracks. We don't have any vias in here except the connections from these pads down to the ground plane. And then we have this version here, which is identical top copper geometry, and we just deleted the cutouts in the ground plane. And then over here, this is a version with the older unoptimized fan out where we come out of the balls mismatched and we come all the way down here with the significant phase error. And then only when we hit these big meanders, we get a big impedance bump and then finally end up in phase coming down here. So here we are in the current density view. At the moment, we have the new version of the layout with the curved fan out to the left rather than the north-south. What we're looking at is current density at 35 gigahertz. I chose the highest frequency in the sweep because the wavelength is smaller and it makes some of these fine details easier to see. And we're looking at a single phase point within the animation. We're going to play it continuously in a minute, but it's easier to narrate when I can point to specific features. So right here at this spot, we can see this is the darkest color that indicates the lowest current density. So this would be a inflection point in the sine. So at the peak or the trough, the voltage is not changing, so we have zero current flow. And then down here, we have the highest current density. So this would be at a zero crossing where dVdt is at the maximum. And then if we zoom in a little bit more, we can see the individual mesh cells and skin effect along the edges of the traces and so on. So with the animation turned on, we can see that the feed lines are driving the BGA lands in phase. We are looking at absolute magnitude here, not a signed value, and so a minimum and a maximum are going to show up as the same color. They're both a larger offset from the zero crossing. And so coming in from here, we're in phase. We come down around, and we can see there's a slight phase shift as we come around this bend because the outer path is a little bit longer than the inner, but it's not quite completely compensated because we don't have a meander here. Unfortunately, within the BGA ball field, that's a little bit challenging to do. And then as we come down here, we have this second meander, and this is actually compensating for both this bend here as well as this one here. And it looks like we actually have a little bit of a shift. We are not quite perfectly aligned coming down here, so probably should have one more meander here and then maybe make this one a little bit smaller. So there's a very slight phase shift coming off of there. And then going down to here, again, same thing. There probably could be one more here to align things a little bit better. And then coming down to the bottom, we're in near perfect alignment coming through here. And then we've got these couple of meanders correcting for the phase at these corners. And then as we come down and finally hit the Arc 6 launch, we are in near perfect phase. Then compare this to the original fan out, and the difference is pretty substantial. Again, coming into the BGA lands in phase, coming down here, we now have a huge phase shift coming down this long vertical run. And then we have the meanders coming through and correcting it. And now we're well phased coming down here. And we come down and again have the same artifacts coming through these corners where we've got a slight misphased area here. Again, probably can tweak that, but I didn't want to change too many variables in one simulation, so I only adjusted the fan out on the BGA side. And then coming down to here, and again, we're in near perfect phase alignment after we get around this last bend. This is a feature that I would really like to see more engineers use, especially when you're starting out and learning and just trying to kind of get a feel for the behavior of transmission line structures and so on. And especially when you're trying to do phase matching of differential pairs, being able to actually see the waveforms propagating down and looking at how the phase shifts as you go through meanders and curves in the trace, I find is a really helpful tool just for getting a better understanding of the behavior of this stuff. And again, we are looking at, this is not a time domain pulse propagation simulation here. Sonnet is not a time domain solver, it's a frequency domain solver. And so we are sweeping the phase of a 35 gigahertz tone here and looking at the wavefronts as they move down at a single frequency point. And so, for example, I can jump down to, say, 10 gigahertz, and we can see the wavefronts are much further away. And so if I'm looking in general for transmission line behavior and just looking for matching within legs, I usually will use the highest frequency of the sweep because it makes small phase shifts a lot easier to see. But if you are interested in behavior at a specific point, or you're trying to find standing waves or something like that, you may actually want to, like a resonance or something like that will show up really nicely at a particular frequency. And then, of course, we can also jump down to the ground plane, and it's a little bit slower because we have more mesh cells here to animate. But now that it's loaded fully, we can see the propagation coming through here. And again, we're looking at the return current behavior here in the ground plane. And I find sometimes looking at the return currents can actually be a little bit better than looking at the transmission line structure when your lines are narrow, when you're trying to kind of get a big picture sense of how everything is propagating. Like if we're zoomed out all this way and we're looking at the signal layers, it becomes a lot harder to see subtle phase shifts. Whereas here, because the return current spreads out a little bit more, you have more mesh cells lit up, it's kind of like putting a big bubble around all the wavefronts, and it makes it a little bit easier to see the small shifts. Like we can see here, there's still a slight phase error coming down here, and we can see there's a big misalignment coming up here, and we're pretty much aligned down here. And that's a little bit harder to see at this big picture level if we're looking up at the signal layer, just because especially like if you're not viewing this in full 1080p HD, it's probably going to be a lot harder to see these wavefronts moving down. And so that's where ngscopeclient comes in. And so I've imported the touchdown files from all of the Sonnet extractions of each of these different layout versions. And we can see here we're simulating a PRBS 31 at 28 gigabits per second. We are injecting 500 femtoseconds RMS of random jitter, not putting any periodic jitter in because I don't need any of that. And then we are turning that into a plus or minus 200 millivolt NRZ signal with a 10 picosecond transition time. So near ideal. Obviously the real SERDES is slower. I'm not doing a full IBIS AMI model here. I'm just treating this as a ideal source going into the channel for the purposes of comparison. Then we're adding 5 millivolts of noise, and then we do our GPU accelerated channel emulation on the touchstone file, run the CDR and the I pattern, and also just loaded the various touchstone files into a memory filter so we can look at all of them on top of each other. And then the other thing I did, so the time domain view for I patterns and so on is running off of the extracted S21, and then moving down to here, we have a ideal step with a infinitely sharp rise time from 0 to 1 volt, and then we are feeding that into channel emulation of S11, and then extracting the impedance transform off of the TDR trace, and then plotting the various versions there. So looking at this is the I pattern going through the currently loaded touchstone file, which is the final layout. So this is what we've simulated the I is going to look like coming out of the ARC6, so right at the ARC6 connector mating plane with the FPGA sourcing an ideal waveform. And we can see this actually still meets the SFF 8431 transmit I mask, which is good because that's what we want. And then we still have to add the insertion loss of the cable on top of that. And so we'll see, I may have to add a retimer or something before we actually get to the optic. We'll figure that out once I get actual measurements, or maybe run an AMI simulation at some point later on with the actual FPGA transceivers. There is no emphasis in this waveform. This is just an ideal, essentially 10 picosecond rise and fall time coming out of the simulated source and then going into our channel and then coming out the far end. And again, this is just at the ARC6 mating plane. We have not added the insertion loss of the cable or any of the stuff on this little breakout board here coming from the ARC6 out to the SFPKs, and so it's probably going to add another quarter of a dB or so of loss at least at the connectors, probably a little bit more. I haven't actually looked up what the mated insertion loss of the ARC6 is. It's in one of these Samtec data sheets. They have a bunch of PDFs. Anyway, so now here we have those 3 simulations with, this is the S21 plots versus frequency simulated out to 35 gigahertz. And right off the bat, you'll notice that the old and the new fanouts are not that different. The main difference is, I think, mostly as far as mode conversion goes, and we're not really seeing that as much in the insertion loss plot, but they're pretty much neck and neck. At any one frequency, there might be a slight spot where one is half a dB or so better or worse than the other, but they look pretty similar here, and it's really the return loss where you can see the difference between these two. But the version without the ground plane cutouts looks awful. We can see we've got these huge ripples in the insertion loss, and then as we get down to 35 gigahertz, we're down to 8 dB of insertion loss, whereas the other ones are around 3 or 4. So we have an extra 4 dB of insertion loss just from all of these reflections and mismatches. And so obviously the cutouts are absolutely key to getting any kind of remotely decent performance. And then the difference between these two ultimately is really going to come down to how much work the DFE is going to have to do in the transceiver, because these are pretty close as far as insertion loss goes. And then moving down here, looking at the same signals and the same colors, we're now looking at the TDR transform. So the version with no cutouts at all obviously does not look great. We have a dip down to about 77 ohms. Again, coming in from the left side, so the BGA launch is right here, coming at about 100 nanoseconds, which is where the position of the step is. And then down here, we have the second massive mismatch at the ARC6. And so, obviously, this version is awful. We can also see there's another bit of a jump up here, which is the same as in the final layout. We'll get to what that is in a second. And so, the next trace we're going to look at after the original version with no cutouts, this is the old fan out. And so, this version has a slightly larger dip at the BGA launch, and then it oscillates a little bit. And then we have this big jump up here. And so, this section right here, where we've got this about 50-ish picoseconds compared to the 350-ish picoseconds of the entire round trip. And so this is about 1/7-ish of the overall trace length. And if we go over to here, we can see right about here, that mismatched length is right about that length. And so we are looking at this section right here where the diff pair is not well phase matched between the coupled legs, is showing up as a large bump in the impedance up to around 113 ohms here, because we're not seeing as much coupling with our partner as we should be. And then down here, there's another couple of sections where the impedance is not really that happy, because again, down here, we've got a few spots around the curves that are less optimized. And up here, so I may actually want to fine tune right about here. We can see that there's a slight shift here where it's not perfectly phased because we've got the mismatch from this curve right there. And so then in the optimized version, the layout that we see in the red, we can see there is still that one small bump up there. And I may still have to tweak this a little bit more, because I think what is going on there is probably right here. I think it's probably that mismatch there, or possibly this bump here. I might need to make that trace in the meander just a little bit fatter. And so right over here, we can see that the trace coming out of the meander is only a couple of mesh cells wide. And so it is entirely possible that we don't have the best fidelity for the size of this, but I think I probably want to make this track a little bit wider and then run the full simulation and see, because I bet that's where that mismatch is. If I really wanted to, I could go and actually measure the linear length of the trace from here out to here and see just how long it is. The other possibility is, again, I could try and put a smaller meander up here. So there's still a little bit of fine-tuning to do, but I just thought it would be interesting to show the results to date and see how much of an improvement there is. And again, this is only about a 10% mismatch. It's not nearly as bad as there. The eye is still wide open, so realistically, this much mismatch is probably something the DFE at the other side is going to have no problem dealing with. But I've waited 13 years to get this far, and I'm going to take as long as it takes to get a impedance profile that I'm satisfied with, and probably simulate a couple of these, not just this one. And once I'm really satisfied everything is good, then I'll go send it out to Fab, and then I can get started bringing it up and writing firmware, and we'll see how it goes. And certainly I'll have more video and or blog stuff about the bring up and doing all the signal integrity verification and tweaking equalizer coefficients and everything to get the most wide open eyes that I can get at the optic. But that is going to be a problem for several months from now. So thank you for watching, and I hope you enjoyed.